talk some more about the definite integral. That's what we were doing last time. And we had just finished doing an example of finding the definite integral by taking the limit of the Riemann sums. I want to do one more example like that, and then I got one for you all to try. These are pretty involved. There's some, I don't know if I'd say it's like super hard. It's just you sort of have to remember a few formulas, and you have to do it without messing it up, which can be a little tricky sometimes. I tried to write down here all the formulas that you need to know. So we got the delta x and the xi. These are the individual points that you use in the Riemann sum. And I suppose I might as well write out, like, the formula for the Riemann sum is this. I equals 1 to n, and it's f of xi times delta x. That's the base times the height. This is the sum of the total area of the rectangles. All right. And then these guys on the right, you have to use in order to evaluate that sum before you take the limit at the end. Anyway, let's do an example, and then, like I said, I got one for you all to try. Let's try find the integral from 0 to 4 of 2x squared plus 1 dx. All right? This actually means the area under the curve of some weird shape. It's not too weird, I guess. That equation there makes a parabola, some kind of parabola, and it's the area under that parabola from x equals 0 to x equals 4. But you don't have to think about that at all to compute the integral as a limit of Riemann sum. So this I'm going to just, maybe over here I'll write down, in this particular example, what is delta x, and then also what is the points, the little x sub I. Delta x is always b minus a over n. So this is 4 minus 0 over n. Now in an example where I tell you the n, you would plug it in, but when you're finding the integral, you have to leave the n as a variable and eventually take the limit at the end as n goes to infinity. Anyway, 4 minus 0 over n, simplify this as much as you can. It's just going to say 4 over n, right? And then the xi is, this is what I've told you at the beginning, a plus I delta x. The a is the lower limit, the lower endpoint of the interval from 0 to 4 here. So it's 0 in this case. And then plus I times delta x, which is 4 over n. So this would, just to write it as simply as possible, 4i over n. That's the delta, or that's the xi in this case. All right, so let's see if we can plug this in. You know, this integral, the definition says lim n goes to infinity of Rn, which is the sum, I equals 1 to n, f of xi delta x. All right, that's the definition of the integral. Sorry, I'm off the bottom. That's the definition of the integral as a Riemann sum. And everything that comes next is just a bunch of plugging stuff in and simplifying and eventually taking the limit at the end, which is a bit of a journey because there's just a lot of steps to it. But, might as well start plugging in. So the n will always, and the n and the I will always stay as variables here until the very end. Plugging in f of xi, I'll leave the f like it is for now, and then xi is, I wrote it over here, 4i over n. So stick that inside the f of 4i over n, and then times delta x, which is 4 over n. And we got to continue to simplify. Plug in for the f, all right? This is sometimes a little tricky, but the f is this function, 2x squared plus 1. And you need to plug in 4i over n. That means you go up to this formula, you write this stuff, but you replace the x with 4i over n. It looks like, all right, I still got all this stuff. Would you please write the whole thing every time? I know some people just get so anxious to write as little as possible and just write like little pieces here and there. It looks crazy when you show somebody else that kind of thing. I would appreciate if you write the whole thing every time. Anyway, f of 4i over n. I'm plugging into the function, which was 2x squared minus 1. So it should look like 2 times this thing squared minus 1, right? That was the function, 2x squared minus 1. Instead of x, I'm plugging in 4i over n. All right, and then all of that, you need parentheses here because it's all multiplied times 4 over n. All right, keep going with the simplifying. I suppose we can do that squared on the inside. Square the fraction. That involves just square the numerator and also square the denominator. Everything in there gets squared. So it'll be sum I equal 1 to n, 2 here, and then when I square that stuff, I guess it's going to be 16 I squared over n squared minus 1, still, times 4 over n. And then I'm going to distribute the 4 over n across that stuff. Okay. Got the lim, the sum. All right, distributing 4 over n. Would you mind if I do this also? 2 times 16 is 32, and then multiplying by 4 is 128, I believe, because I know my powers of 2. 128 I squared over n cubed now because I multiplied it by 4 over n. So I get another n on the bottom. And then minus, I'm distributing here, so 4 over n times 1 is, again, 4 over n. All right, we're getting there. Yes?
Isn't the original equation plus 1?
Oh, is it plus 1? Yeah, it is. Thank you for that. So all these minus 1 should be plus 1s. I'm glad you corrected me before things got nasty. They didn't, maybe they got nasty already, but it's easy to fix at this point. Thank you. Any other suggestions? All right. Okay, what's next? I want to do these sums. You want to break up the sum so that it looks like these guys, right? These things, because we have formulas for those things. So when I look at this here, I like the looks of this I squared. I want to sort of like strip away everything else that's around that I squared. So first of all, you have two parts which are added together. I'm going to split up the sum across those two things. So I split it up as the sum of the first one over n cubed plus the sum of the second one. And then from each of those two parts, I'm going to factor out the constant and also the n. The n can factor out of the sum. The n can't pull all the way out past the limit, but it can factor out of the sum. So from the first one, I factor 128 and n cubed on the bottom. It looks like 128 over n cubed, the sum of I squared. And then the second one, I can factor everything out of that, 4 over n. I think of this as 4 over n times 1, and so when it comes out, what's left over on the inside is just 1. And then each of those two sums, we use the appropriate formula that I wrote in the box at the beginning. So the sum of I squared, I happen to remember, and I hope you have this written down somewhere. 128 over n cubed. Okay, and then the sum of I squared is n times n plus 1 times 2n plus 1 over 6. That one I will not expect you to have memorized, but you should know where to look for it. And then 4 over n, the sum of 1, I do expect you to have that one memorized. What's that one? This is the sum 1 plus 1 plus 1 plus 1 over and over again, n times. It is n. Yeah, that's the easiest one of all. You don't even really have to memorize it. That's sort of a common sense thing. If you add 1 plus 1 plus 1, n times, you get n. All right, we're almost done here. We have simplified everything away, and now we're basically at the point when we can do this limit. Maybe I'll just simplify a little bit. These ends cancel here, right? So that's just going to be 4 in the end. And then this one I'm going to write as, lim. All right, 128. Maybe I'll just sort of put the 128 by itself. And then what I have over here is n times n plus 1 times 2n plus 1 over 6 n cubed. I just want to put the n's together. So I put the n cubed in that denominator. And then it's out here is a plus 4. That was left over from the 4 over n times n. And now, finally, we can take the limit. When you do the limit, this thing right here, you think of this as a ratio of polynomials, which it is. And on the bottom and the top, we both have degree 3. In such a case, the limit is equal to the ratio of the coefficients on front of the third degree term, which in this case, on bottom, the coefficient is 6. And on the top, I'm not going to bother multiplying this all out, but the coefficient will be 2 on the front because you have this 2 here. The n cubed term on the top will be n times 2n. Yeah?
Did you distribute the 128 before taking the limit?
You don't have to distribute it. You mean across the 4 also, or just up here?
Just up there.
Yeah, this is all multiplication, so it's not really appropriate to distribute.
Oh, I just meant like,
Put it in the fraction, maybe?
yeah, because instead of getting 2 over 6, you would get like, 200 and, what is it,
Yes.
256?
That's right. But the way I was going to write this is what I get is 128, and then this fraction, when you do the limit, it becomes 2 over 6.
Oh, okay.
And if you could also put the 128 inside the fraction, then you would have got whatever 256 over 6, which is the same as this. So, yeah, there's a few different ways you can compute the intermediate steps if you want. All right. Anyway, that's the answer. 2 over 6 is 1/3. I don't want to bother simplifying that any more than that. It's 128 times 1/3 plus 4. This is the answer. All right. It's a bit of a journey to get there. That took 10 minutes, and I felt like I was going kind of fast. That's because we just did one at the end last time, just like this. I don't know if you felt like I was going kind of fast. Any questions about that? I got one for you to try out, so if you do have questions, I will, ask me as I'm walking around. All right, let's try. How about this one? For this integral, 2 to 4 of 3x minus 2 dx. I got a little two-parter here. Part A, find R8 and L8. These we talked about last time. I haven't refreshed our memory about this, but remember, this means not doing the limit of the Riemann sum. So just individually, if I took the Riemann sum using 8 terms, remember R8 means you use the right-hand endpoints. L8 means you use the left-hand endpoints. I will just very briefly refresh your memory. How I would start that would be draw out chart out the interval from 2 to 4, break this into 8 pieces, figure out where all those points are, and then for R8, you use the right-hand endpoints and you plug into the function and add it all together. All right? And for L8, you would use the left-hand endpoints, which are the other ones, and add it all together. And then also, so part B is actually, find the integral by doing that what I just did. Lim n goes to infinity of Rn. All right. See what you think. The first part, if you really want to get the final answer, you might want to use a calculator, but I would say don't bother doing that unless you really want to. You can just write out what you would have written and don't plug it into your calculator. All right. See what you think. I will give us some time. I'll walk around. The first part's easier, but you have to remember how to do it. can feel free to use the dot when you're writing. It's annoying to write R8 all the way out. Yes? Yeah. Let's take a couple more minutes and then we'll see if, I'll see if I can do these.
Yeah.
Getting work? All right, I'm going to start doing these. I know not everybody has finished, and that's okay. Let's talk about the first part. The R8 will be the adding together the areas of the rectangles, 8 rectangles, using the right-hand endpoints. The way you want to do that is set up the interval. This is what I did before. It's from 2 to 4. And since I said R8, that means you should split this interval into 8 pieces and try and figure out where all those points go. The midpoint, I guess, will be 3, right? Because that's, I know the midway in between 2 and 4 is 3. And then the distance from 2 to 3 is being divided into 4 equal parts. So that means this really has to be like this. 2.25, 2.5, and then 2.75, right? I'm just sort of trying to use common sense to figure out where those intermediate points are. If you don't like that, you can always compute the delta x is b minus a over n. In this case, that would be 4 minus 2 over 8. That's the b and the a are the 4 and the 2. And that is 2 over 8, which is 1/4, which means the width of each little bit here is 1/4. And that is what it is when I figured this out. If you're having a hard time figuring out where those points should be just by common sense, you can always work out the delta x this way, and that will tell you where they should be. The next point is 3.25, and then 3.5, and then 3.75. All right, anyway, I'm going to, since it's R8, I'm going to, in each of those little bits, I choose the point on the right-hand side, right-hand side. And then I'm just going to add together a whole bunch of things, and each thing shall be delta x times f of whatever the number is. So I'm going to do delta x, which is a fourth, or 0.25 if you like. R8 is 0.25 times f of the first point, which is 2.25, plus 0.25 times f of the next point, which is 2.5. You're just adding every point together. Each time you multiply by delta x, and you plug that value into the function. As I said before, you can put the dot, dot, dot. This is very tedious to write all the way out. If you're going to use a dot, 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 you should at least give me the first two so that I can understand what the pattern is supposed to be, and then give me the last one so that I know that you know where to stop. In this case, since I'm doing the right-hand endpoints, I should go all the way up to 4. F of 4, all right? If you're doing this on a test or something, you're not going to be able to actually evaluate this on your calculator, which is fine. I would like you to write one more step, which is don't leave the f's in the answer. I want to know that you know what the f is supposed to mean. What the f means in this example is it's this function here, 3x minus 2. So every time I see a f, I'm going to do 3x minus 2. So this will be my final answer, 0.25 times 3 times 2.25 minus 2. And then the next one, 0.25 times 3 times 2.5 minus 2. And then, etc. The last one, 0.25 times 3 times 4 minus 2. All right, this is R8. I hope everybody came up with that eventually. This is something I know we talked about at the beginning last time. This is really not difficult. You just have to know how to set it up. You don't have to do much actual thinking about it. All right, great. This was R8. Make sure you have those parentheses in there. If you left those parentheses out, it means something different. The 0.25 really would distribute across this whole thing. If there were no parentheses, then it wouldn't distribute, and it would be different. What about L8? R8, I looked at these 8 little bits and chose the point on the right every time. L8, I look at the same 8 little bits, but I choose the point on the left every time. The effect is I'm going to get almost exactly the same answer, except the first point will be 2, and it goes all the way up. The last point will be 3.75 if I use the left-hand point. So would you mind if I just jump right to that? L8, it's the same thing, only the precise points are different. You start with 2. And you include the 2, but you exclude the 4. So it will say 0.25, 3 times 2 minus 2, plus the next point would be 3 times 2.25 minus 2, etc. And the last one is 3 times 3.75 minus 2. Like that. I hope this is what you got for the R8 and the L8. This, I say, is easier. I actually think these are very easy. You just have to... like I said, you just have to know what to do. In particular, it doesn't matter how hard the function is, how complicated the function is, because you don't do anything to it. You don't take the derivative or the antiderivative or anything. You just plug the numbers into it. So it really doesn't matter what the function is. All right, any questions about that? Okay, I don't want to spend the whole time on the easy part. Let's do the hard part. That is the actual integral, 2 to 4, 3x minus 2 dx. All right. We should start by finding the delta x. It's b minus a over n, which is 4 minus 2 over n, which is 2 over n. All right? And then we find the xi. It is a plus I delta x. This is a is 2, so it's 2 plus I times 2 over n, which you can write a little nicer as 2 plus 2i over n. I hope that's what you got. I saw a lot of people starting off right. Okay, then the integral is lim n goes to infinity of Rn, which is the sum I equals 1 to n, f of xi delta x. Plug everything in. The sum I equals 1 to n. So it's f of 2 plus 2i over n. And then delta x is 2 over n. How am I doing so far? No complaints. All right. I'll keep going then. And, oops. The sum I equals 1 to n Okay, I plug into the f. This is maybe slightly tricky. 3 times that stuff inside the parentheses minus 2. It's got to look like this, and make sure you get your parentheses right. 3 times 2 plus 2 over n minus 2. And all of that times 2 over n. I hope that's how you plugged it in. Okay, now we just got to, expand, distribute, whatever, simplify everything. I'm going to first distribute the 3 on the very inside of the parentheses there. I equal 1 to n. All right, distribute the 3. I got 6 plus 6i over n. That stuff, I guess I no longer need those parentheses. Minus 2. I do need these parentheses. All right. The next thing I'm going to do is distribute that 2 over n. Although, before that, we could just combine the 6 minus 2 on the inside and make that a 4. That'll simplify a little bit. So, all of this. 4 plus 6i over n. All of this times 2 over n. All right, let's do it. Distribute the 2 over n. We're almost there. 4 times 2 over n is 8 over n, plus 6i over n times 2 over n is 12i over n squared, right? What should I do next? I know some of you worked this all the way out. What'd you do next? Yeah?
Separate it into 2 different.
Yeah, break up the sum into 2 different sums. So it's going to be the sum I equals 1 to n 8 over n plus the sum I equals 1 to n 12i over n squared. Great. Then in each of those sums we should factor out all the garbage, leaving inside only the i's. In the first case, you can factor everything out. So it's 8 over n, the sum of 1. And in the second case, you can factor out 12 over n squared. And it remains the sum of I. And then you just use your summation formulas that you remember. In this case, you don't need any of the fancier ones. These two, like I said last time, I will expect you to remember these two for the test. We get 8 over n times the sum of 1, which is n, plus 12 over n squared times the sum of I, which is this, n times n plus 1 over 2. Right? Those n's cancel this 8 over n times n, so we're just going to get 8 at the beginning there. 8, and then plus, this is going to be 12 over 2 is like 6, and then the n stuff is this. And when I take the limit, that fraction of n's becomes 1. That's because the top and the bottom are both degree 2, and their coefficients on the front term is 1 each time. So I think my final answer is, oops, I don't have to write the lim anymore, since I'm doing the lim in this step. 8 plus 6, 14. Anybody get 14? That's what I got. I hope you got 14 eventually. There's, of course, many chances in there to mess it up. Don't mess it up, is all I can say. I am just as likely to mess it up as you all are, as you know by now. All right? Any questions about that? This is, like I said, I mean, it's hard just because there's a lot of chances to screw it up. Although there's not really a hard idea behind it. You just got to work it all out. We got 10 more minutes. Like I said last time, this, after today, we're going to regard this as the hard way to do the integral. There is a super awesome trick which allows you to do integrals much, much faster than all of that. Just like with the derivative, there was sort of a hard way to do the derivative, and then you learn some tricks. In my opinion, this hard way to do the integral is like even harder than the hard way to do the derivative, which makes the trick so awesome. So we got 13 minutes. I think we can at least start discussing the awesome trick. We're not going to belabor this Riemann sum thing. You'll do some on the homework. You should expect to do one of those on the final exam, but we're not going to really do them much more than that today. If that's all right with you all, I think it probably is. Let's talk about the awesome trick. It's so awesome that it has a very important sounding name. It's called the fundamental theorem of calculus. The fundamental theorem of calculus. This is the trick to do the integral. Basically, calculus, as far as the integral is concerned, would be way too hard if there was no such trick. Same with the derivative. The reason that like human beings can do derivatives comfortably is because of the awesome tricks for the derivative. There is a trick for the fundamental theorem of calculus. I will just say the trick to do integrals. We're not going to get to the trick within 12 minutes, but we'll start on the journey, all right? There's actually two different ways. I should say more specifically, it's the trick to do integrals without the Riemann sums, right? That's the thing that we're trying to avoid here. The Riemann sum is what we just did, the thing where you do the limit n goes to infinity of the sum of f of xi times delta x. There are actually two different ways of saying the fundamental theorem of calculus. There's sort of a weird way of saying it, and then the one which we will come to know and love deeply. We're going to start actually with the weird one because it's weird, but it's actually easier to explain why it's true. So this is called, so I will just say there's two versions. They both, behind the scenes, they mean the same thing, but it's sort of two different ways of saying it. And we're going to start with the stranger one. So number one, the fundamental theorem of calculus, the first version. Our book calls it, actually, I'll say it the cute way they say it, FTC number one. That means fundamental theorem of calculus, the first version, is about something that probably nobody ever wonders about, but it's about functions that look like this. G of x is defined to be the integral from a to x of some other function, f of t dt. This is very weird, but the idea is you start with one function f, and you make another function by sticking f inside of the integral sign and putting the variable up top. Usually the integral we write like from a to b, or from one specific number to another, but this has the variable inside the integral sign boundaries. What this means is this is the area under this function, f of t, up to x. I'll try and draw some pictures to explain what exactly I mean by that. You have to imagine I have some function, f of t. So let's say it looks like that. This is f of t, all right? G of x is the area when you start at a and you go up to whatever x is. So the area, let's just imagine if the a is 0. That means, and I'll mark off some points here. What is g of 2? Would be the area up to x equals 2. So on the picture, that's this. You take the area going up to where x is 2. All right, so that right there, that's g of 2. What would like g of 3 be? It would be the area that you get if you go all the way up to 3, which in this example will be a little bit bigger, right? I'll try and write that down. I'm trying to draw the same picture here. Same function, f of t. G of 3 on the picture would be this area. Right, that area is g of 3. I tried to draw the same picture again. It doesn't look quite the same, but I hope you get the idea. G of x, it represents the area under the curve when you go up a certain amount, up to whatever the x is, all right? And the fundamental theorem is about that weird function g, the area up to a particular point. And the fundamental theorem of calculus, version number 1, is about something even weirder. It's about this, the derivative of g of x. That area up to a particular point. This is 3. I meant to label that. The area up to a particular point. Find the derivative of that function. If you thought this is a weird function, this is even weirder. This, if I were to write it all the way out, it would look like this. The derivative of the integral from a to x, f of t dt. All right? Very strange looking. The fundamental theorem of calculus is about that. The derivative of the integral. So what this would mean, I'm trying to think about this in ordinary language. I'll draw that same picture again. This is f of t, right? And g of x would represent, if I just took the area up to x, right? G of x is that area. It's the area when you go up to x, right? This area is g of x. And what does g prime of x represent? Well, it's the rate of change of that area. It would mean if I were to change the x a little bit, how much would the area change? And you can say a little bit more specifically, g prime of x, remember the definition of the derivative? We're not really going to get into this in detail, but it's this, right? G of x plus h minus g of x over h. It has to do with if I were to change the x a little bit, increase it a little bit to x plus h, how much would that area change? It's this. I'm going to try and draw this in a different color here. If you increased the x a little bitty bit, then how much extra area would you get? That's what... Did that screen just turn off? Sorry, folks on that side. I don't know why that happened. I hope you can still see the one in front. This blue region here, g prime of x, measures this area, right? When you change the x by a little bit, how much will the area change by? So this thing here, the derivative of g, or this weird derivative of the integral, what that means, what it represents is how fast, or it's sort of how big this blue chunk is when you increase the x a little bit, all right? And the fundamental theorem, I'll give you the sort of intuitive version now, and then we'll talk about the real sort of details next time. I would like you to notice this blue area there, g prime of x. G prime of x depends a lot on f of x. Let me see if I can convince you of that in our remaining 4 minutes. I can draw the same picture again. Sorry, let me say, how about this? If f of x is big, then what does the picture look like? Well, f of x is just the y value at x, right? So let's say f of x is big. That would be this y value. So that means the function looks kind of like that, right? This is f of x, all the way up there. If f of x is big, then what is g prime, remember, represents that sort of thin blue area. And on this picture, it would look like, get my blue. Look like this, right? This is g prime of x. Measures this area, right? That's what it looks like if the f of x is a big number, just the y value where x is a big number. That little blue strip looks like that. Pretty tall, kind of skinny, but pretty tall. Like me, right? What if f of x is small? What if that y value is not like way up there, but it's much smaller? What would that look like? Well, I don't know. Let's see if I can draw that. Unfortunately, I can't keep both of the pictures on. So that would mean that it was something like this, right? The y value at x is way down here. This is f of x. All right. Then what does the picture look like? Well, then the blue thing is actually quite small, right? It's only this little bit, right? What I'm trying to convince you of is that the size of the blue thing is actually very closely related to how high up the function is at that specific point, right? So the blue thing, which represents g prime of x relates to f of x. In particular, the first picture I drew, if f of x is big, then g prime of x is also big, right? It was that big, tall blue thing. And the second picture I drew, if f of x is small, then g prime of x is also small, right? It's that little blue thing. So there is a relationship between the two things, and I'm going to tell you, and this we will discuss. What I've said so far really is not enough to convince you fully, but we'll discuss this next time. Actually, these things which are related, g prime is related to f of x. In fact, g prime of x equals f of x. They are equal. They are the same number, all right? And so if I were to write out the whole like big and nasty version of g prime of x is this. It's the derivative of the integral a to x, f of t dt. And what I'm telling you is it is equal to f of x. And that is the fundamental theorem of calculus part 1. This is FTC number 1, all right? The very, very informal way of explaining this, when your friends at dinner ask you, what is that fundamental theorem of calculus again? One very informal and not terribly accurate, but you get the idea across. It kind of looks like in this formula, this derivative cancels the integral sign, and all that's left is the function. In this sense, the derivative is kind of the opposite of the integral sign. This is sort of a deep fact. Anyway, we'll talk about that more next time. That's the idea of it. See you then.